Welcome, students. We're diving right in today because I wanted to put together a really comprehensive explainer for you to capture all the critical components of Risk and AI Module 1. You can basically use this explainer as your ultimate educational roadmap. We are going to bridge the gap between technical AI possibilities and your actual real-world business needs. By the time we wrap this up, you'll have a beautifully structured idea of what Module 1 is all about and, more importantly, exactly why it matters for your career. So here's our agenda for this module. We're starting with classical AI and its limits, then we'll move on to the deep learning revolution. From there, we'll break down the 4 types of machine learning, and finally, we'll dive deep into the risks of modern AI. All right, let's kick things off with Section 1, Classical AI and its Limits. We have to start our academic journey with what's affectionately known in the field as good old-fashioned AI, or GOFI. This early era was entirely about explicit, precise processing and very strict logical rules. The whole idea was based on the belief that human intelligence could just be perfectly codified step by step. The goal back then was essentially to map out human logic to conquer intellectual games and prove mathematical theorems. It really started back in 1936 with Alan Turing's theoretical machine, a universal computer that could follow any logical recipe. That directly led to 1956, where John McCarthy actually coined the term artificial intelligence at that famous Dartmouth conference. And the absolute crowning achievement of this era, that was 1997, when IBM's Deep Blue defeated world chess champion Garry Kasparov. It was just an incredible triumph of explicit programming and rule-based search. Now, the elegant mathematical machinery that powered that classical era relied heavily on techniques like look-ahead. Think about how you play Sudoku, right? You trace the logical implications of writing a certain number in a specific cell. And then there's recursion. This is where a really complex problem is solved by progressively reducing it to simpler instances of the same problem. Think of the Tower of Hanoi puzzle, where you have to move disks from one peg to another without ever placing a larger disk on a smaller one. Instead of just blind guessing, classical AI used recursion to search through a massive tree of possibilities, progressively breaking that huge problem down into tiny, solvable, single-disk movements. But here's where the classical approach hit a massive roadblock. While good old-fashioned AI worked absolute wonders in games of perfect information, like chess, it failed spectacularly in the ambiguous, super messy real world. We call this the frame problem. Basically, when you try to program every single logical rule for a dynamic environment, you hit what's known as a combinatorial explosion. The sheer number of possibilities and exceptions just grows exponentially, totally overwhelming the system. The real world simply doesn't play by rigid rules, and that limitation paved the way for a radical shift in how we teach machines. Which brings us nicely to Section 2, the deep learning revolution. So this revolution was a total paradigm shift. It was inspired not by rigid symbolic logic, but by human biology, specifically the intricate webs of neurons in our own brains. Instead of human programmers sitting down and writing every single logical rule, neural networks are actually designed to teach themselves. And the absolute magic behind this is called backpropagation. Imagine a network trying to recognize a handwritten number 6. If it guesses wrong, backpropagation calculates exactly how much each hidden connection contributed to that error, and then it literally works backwards through the layers of the network, adjusting millions of tiny hidden weights to minimize that error the next time around. The system learns through iterative experience. The crucial takeaway here is the profound shift from explicit logic to implicit probabilities. We completely stopped telling computers exactly how to solve a problem and started just giving them vast amounts of data so they could find the patterns themselves. This is exactly what allowed DeepMind's AlphaZero to master incredibly complex games like chess and Go. It wasn't fed a database of human games to copy. It literally just played against itself for a few hours, learning completely on its own based purely on probabilities and outcomes. But, of course, this amazing capability comes with a severe catch. That massive web of learned weights that allows deep learning to function creates what we call a black box. The information is distributed so implicitly across billions of parameters that even the AI's own creators cannot fully interpret or explain exactly why it made a specific decision. It works flawlessly, but it is fundamentally inscrutable. Moving right along to Section 3, 4 types of machine learning. Okay, to understand how we actually apply this inscrutable black box in the real world, we need to look at the 4 core machine learning paradigms that organizations use today: reinforcement learning, supervised learning, unsupervised learning, and semi-supervised learning. These are the engines transforming raw data into predictive insights. And as future leaders, knowing the difference between them is absolutely critical. If we look at their distinct business applications, you'll see supervised learning heavily dominates areas like credit scoring or image classification, simply because it learns from labeled historical data. Then we have reinforcement learning. This one relies on trial, error, and rewards, making it the absolute perfect driver for things like physical robotics, autonomous vehicles, and high-frequency financial trading algorithms. And unsupervised learning, that takes completely unlabeled data to magically find hidden patterns. Let's actually look at a really fascinating example of unsupervised learning called principal component analysis, or PCA. PCA can reveal hidden clusters without any human labeling whatsoever. For instance, back in 1982, researcher John Burroughs wanted to know if a specific anonymous 18th century novel was actually written by the famous author Tobias Smollett. By feeding the frequencies of just 50 common words into a PCA analysis, the system calculated dimensions of maximum variation and projected them onto a graph. And guess what? The anonymous text clustered perfectly next to Smollett's known works. It found the stylistic fingerprints completely automatically. Pretty amazing, right? All right, finally, let's get into Section 4, the risks of modern AI. Knowing these incredible tools is great, but as future leaders, your primary job is often going to be managing their unintended consequences. Because deep learning is a black box, it poses massive privacy and bias risks. You can't just delete a gender or race column from a dataset and expect to fix a skew, because the AI will secretly learn proxies for those attributes from historical data. Things like a zip code or maybe the sports listed on a CV. And regarding privacy, a 2013 Cambridge University study proved that an AI analyzing simple, innocuous Facebook likes could accurately infer highly sensitive personal traits, everything from your political views to your intelligence and even substance use. The capacity for hidden manipulation here is vast. And this brings us to the very real risk of over-reliance. This is captured so perfectly by Emily M. Bender's phrase, the stochastic parrot. When you use something like ChatGPT, its conversational fluency makes it feel like it really understands you. But it doesn't. It holds zero internal model of the real world. It is merely mimicking textual probabilities, like a parrot just predicting the next most likely word. If a software engineer over-relies on this, the AI might hallucinate programming code that looks perfectly plausible on the surface, but actually contains fatal, really hard-to-detect errors. So let's tie this all together. These are the specific risks you will be directly responsible for mitigating on the job. On an individual level, we're dealing with automation bias, where humans just get lazy and trust the machine entirely, along with severe privacy loss. At the organizational level, a flawed AI model can trigger massive reputational damage and serious regulatory liabilities. And societally, well, we are looking at job displacement, widening wealth gaps, the weaponization of deepfakes, and even existential threats. Remember that adversarial sticker that makes a self-driving car read a stop sign as a speed limit sign? That is the reality of the fragility we are managing here. Which leaves us with this crucial question to ponder as we wrap up this explainer. You now understand the tools, the history, and the inherent dangers of the black box. So as we prepare for Module 2, I really want you to ask yourself, how will you step up to govern these complex systems? How are you going to mitigate these profound risks while simultaneously unlocking AI's immense transformative potential for your business? Keep that thought in mind, and I'll see you in the next module.